Here we're going to use this nice diagram of the orthoclase albite binary from Winter's textbook on igneous and metamorphic petrology to take a look at a different kind of topology in phase relationships. So we have the solvus here that might be familiar from those of you who have seen our videos from our mineralogy series. So if we have a single feldspar here and we let it cool, let's just take a bulk composition here, let's say right there. If we have a single feldspar composition at high temperature, so we have complete solid solution, let's say at 800 degrees, that solid solution is not able to sustain itself at lower temperatures. So if we come down to, let's say, 600 degrees, at this point, this single feldspar will start to break up into two components. We'll have an albite-rich component here that will precipitate out, and we can bring in a vertical line to mark that. So there's our albite-rich component. And we'll have this composition of feldspar that is very close to the bulk composition. It is close to the bulk composition because this amount of albite-rich material is very, very small, infinitesimally small, because this bulk composition has just barely reached the solvus curve. And then if we go to lower temperatures, now the two feldspars are much more widely separated, and we would find the two feldspars by the two intersections. It's not quite intersecting there, too far over to the left. So there we go. So now we've got, for our original bulk composition that was over here, it's broken up into an orthoclase and albite-rich composition. And that gives us that classic perthite texture that we see in minerals, where we see this very sort of uneven white and pink or white and gray striping in many alkali feldspars. Now what happens if we take the system up to much, much higher temperatures? Then we have this system up here that looks kind of like a eutectic, but as you'll see here, it does not exactly act like a eutectic. It will over here at high pressures, but we'll get to that in a moment. And then we have these loops here that look kind of like a solid solution loop, and in fact they work very much like a solid solution loop. So let's come back to this bulk composition that we had around here, around orthoclase, what, 40%? No, orthoclase maybe 60%, albite 40%. So if we had this bulk composition here, it would, if it were completely liquid and we were cooling it, then the first liquid would appear here at about 1200 degrees centigrade. And it would continue cooling as it would do so. Well, let's take a look at that first crystal that would come out. The first crystal, oh, PowerPoint might not let me get precisely the right value, but we're going to get a very orthoclase-rich feldspar. And as we pull out orthoclase components, the liquid will be driven to the right, more sodium-rich compositions. And if we have a more sodium-rich liquid, we'll keep that bulk composition fixed. If we have a more sodium-rich liquid, which we do here, so now the liquid is over here instead of at the bulk composition, then we would get a more sodium-rich crystal as well. So we're still very rich in orthoclase, but not as rich in orthoclase as we were for the original crystal, the first crystal to precipitate out. But take a look at what happens here when we have a crystal that finally matches the bulk composition. We have a liquid that is over here, but that liquid has not yet reached that eutectic-like point over there. So in this case, the liquid will never reach the eutectic. And it doesn't matter whether we start on the left side of this minimum, or if we start on the right side. If we started on the right side, we'd just have the same thing in reverse. So what would happen? This represents the last little bit of liquid to precipitate out. Now we have a solid that is really just that single feldspar that we were looking at earlier. And that single feldspar will simply cool through a pretty wide range of temperatures until it finally hits the solvus, which will happen, well, the way I've drawn it here, it's going to happen a little bit above 600 degrees. And then it'll split up into two feldspar components that we can find by drawing vertical lines that hit the intersection of the solvus. If we started with a bulk composition, let's let this guy be our bulk composition. Then the first crystal to precipitate out would happen at a temperature of, well, just under 1100 degrees. The first crystal to form would be very albite rich. And as the system would cool, we would have the very last liquid to form would be right around here, and then we would have a feldspar equal to that bulk composition that would cool. The liquid would never reach that minimum point, and that single feldspar, let's get that liquid composition out of the way, this single feldspar composition would now cool and would begin to split up into two feldspars at a temperature a little under 600 degrees. The first other phase to precipitate out would be an orthoclase-rich solid phase, and as we lower the temperature, the orthoclase phase would become even more orthoclase-rich, and the albite-rich fellow would become even more albite-rich relative to that bulk composition we started with. All right, let's take a look at this middle diagram. This first diagram is for a pressure of 1 atmosphere, except that atmospheric pressure is not being exerted by a mixture of nitrogen and oxygen gas. It's being exerted by water pressure. So it's as if we have the entire system submerged in a water bath, and then that water bath is put under a pressure of 1 atmosphere. What happens if we increase the pressure on that water bath to 200 MPa or 2 kilobars, 2,000 times atmospheric pressure? We get the same kind of geometry, so that we don't really need to go through any specific examples here. If we had a bulk composition here, well, I guess we can run quickly through it. Notice that if we were going to have a liquid that would cool, that liquid would be stable to a much lower temperature than the case for the same bulk composition here. And the reason why the liquid liquid field has expanded is because that liquid is much more easily able to dissolve the water that is surrounding it in this water bath. So if we start adding a new component to the system, and the higher the pressure we go, the more we're forcing that new component into one of these phases. The phase that can absorb that component is the one that'll have its phase stability field expanded at the expense of the other. So the liquid field expands, and the solid field of single and even 2 feldspars is contracted because the water is able to absorb the changes. It's able to absorb the perturbations that we are exerting on the system by pushing more water against the boundaries of that system. So the liquid now will precipitate out crystals at a much lower temperature, but it will do the same thing. The first crystal over here will be very orthoclase rich. If we continue to lower the temperature, the last liquid would be around there at about this composition and at a temperature of a little under 800 degrees centigrade. And then when we're done, then the solid would simply be, we haven't drawn it very precise here, that final temperature would be, let's see if PowerPoint will let us do it, would be a little closer to 800 degrees. Then we'll have a single crystal of feldspar or a single phase of feldspar. It doesn't have to be one crystal, it could be multiple crystals, but all of one composition, and then they will break up into 2 components as we saw before. What happens here when the water pressure is greater than 500 MPa or greater than 5 kilobars or more than 5,000 times atmospheric pressure? Now this begins to act a little bit more like a eutectic. If we have a bulk composition, let's say that is here, the first liquid that would form if we have something starting at higher temperature would precipitate out its first feldspar crystals at a little under 700 degrees centigrade. The first crystals would be very orthoclase rich. As this system cools, what will happen is now it'll finally reach that minimum. Why? Because that bulk composition, this bulk solid would never reach the bulk composition. It's going to hit that as the solids evolve along this solidus curve, they will hit the solvus before they hit the bulk composition. And when we finally reach this position here along the phase diagram, we'll now have 2 feldspar compositions. So we started out with a liquid here that precipitated out a feldspar composition here, very rich in orthoclase. And as we lowered the temperature, the crystal became more albite rich. And as we lowered the temperature still, the crystal became more albite rich. But once we reach this temperature here, now we have 2 feldspars. So all the liquid will now precipitate out to give us 2 feldspars. one that is over here that is more orthoclase rich, and then one is that is over here that is more albite rich. And now you could see it's acting kind of like eutectic in the sense that all liquids, no matter where they start, will all reach this point here, and they will all end up having a mixture of albite and orthoclase. We're a little bit mistaken. Not all liquids. If we have a bulk composition that is sufficiently orthoclase rich, then what would happen? What will happen is we'd have, let's get these other guys out of the way. We can avoid this if we take very extreme compositions. So if we have a bulk composition, let's say that's over here, we'll try to make sure that we miss it. Our first crystal would form at this temperature, just under 800 degrees centigrade. We have a very orthoclase rich composition that would form. And as we decrease the temperature, notice that we hit the solid as here, and then the last liquid we would get is here, but now the solid can actually match the bulk composition. We'd have a single feldspar, and we don't need this guy anymore. The temperature would cool until that feldspar would just barely hit this solvus. And if we took a more extreme composition, closer to the orthoclase sideline, it could miss that solvus altogether. So I did misspeak earlier. Not all liquids are going to reach this eutectic-like point here. Let's take another example that's very albite rich. Let's say if we can make it work out so that it'll miss the eutectic point. Actually, you can see how ahead of time how we can make this work. So we're going to have the first crystal. If we have a liquid that's cooling, the first crystal is going to come out a little below 700 degrees. That first crystal will be very albite rich, and then as the system cools, we will have crystals that will match the bulk composition as they would here. And now we have a single albite. There's no more, this is the last little bit of liquid here, so the last little bit of liquid is there, but that's going to disappear before we hit that eutectic-like point. And so we'll have a single bulk composition that will cool, and it'll continue to cool until it hits the solvus, in which case now we're going to precipitate out a second feldspar phase, and we'd have two feldspars. So I did misspeak earlier. Not all liquids are going to hit the are going to hit that eutectic-like point. If we take extreme bulk compositions here out on the wings, then that solid is going to be able to hit the bulk composition, and it will allow us to avoid hitting this point here. But liquids that are going to start in this narrow range here in between these two vertical lines, all of these liquids in there will reach that eutectic-like point before the solid is able to match the bulk composition. And so we get that more unusual case that we started out with. So that is the case at 500 MPa or higher when we have a much higher pressure, total water pressure, much greatly expanded liquid stability field, because again, liquid is able to absorb those water components, whereas the feldspars are not. And that changes the topology for us and how we interpret these diagrams.